Unit 3 Chemistry, Chapter 2, Part 2, looking at how we can use delta H values. There's a couple of different ways. One is that we can use them to make reaction pathways or to look at the enthalpy change over a reaction. Okay? So if we know that we are going from A and B to make C, and then we're going to break C down to make D and E, okay? We know the enthalpy change for that first step. A plus B gives us C. We know that takes in 50 kilojoules of energy. We know that if we had C and we made D and E, it's going to take in a further 100 kilojoules of energy. So therefore, we can say that if we're going from there all the way to there, we're going to take in a grand total of 150 kilojoules of energy. Okay? We could also do the same thing, but we're reversing one of those reactions to make our overall equation, in which case we'd simply switch the sign. If we needed to double one of the reactions, then we would double the value of delta H. Because remember, this is per mole in that equation. If you double the coefficient in the equation, you've got to double your delta H value. The other thing we can use a delta H for is we can use it to look at exactly how much energy is released per mole of a particular thing in there. Okay? So if the delta H for the formation of 1 mole of water is 572 kilojoules a mole, if we double the coefficients, then we double that delta H value. The other thing we can use our delta H values for is to draw energy profile diagrams. Okay? And we'll come to this in a sec. If we look at our energy profile diagrams, we've got a couple of things on there. We've got the heat absorbed or taken in, that's our delta H value, or the heat given out to the surroundings. The second thing we've got on all of them is our activation energy. Now, activation energies are always positive. Okay? Activation energy is how much energy is needed to start the reaction. Okay? All reactions involve 2 steps. Breaking bonds in the reactants, which requires energy. You've got to take in energy to break them apart. Yeah? If you think of it like sort of 2 things bonded together and you're pulling them apart, that requires energy. The reverse process is going to be the reverse. So if breaking things apart requires energy, making bonds is going to release energy. Okay? So activation energy is how much energy is needed to break the bonds in the reaction. And that's why even something like the burning of methane, which happens spontaneously and will keep going, it needs a spark. It needs a match to start it off. That's giving it the energy for the first lot of the bonds in the reactants to be broken. If we know the value of the activation energy and the value of the delta H, then we can plot an energy profile diagram. And if it's an endothermic reaction, then that's going to go up to a high point for your activation energy and then down a little bit for your products. If it's a lower one, an exothermic reaction one, then we'll go up again because we're still breaking bonds in our reactants. But when we make bonds in the products, that releases more energy. So we're going to have a downward slope to a lower enthalpy in the products.